Hello, night travelers, those quiet souls seeking calm beneath the vast orchestra of the night. Welcome back to the Night Observer, a place where weary minds find rest, where comfort is gently offered, and where sleep arrives hand in hand with wonder as we contemplate the immense and mysterious universe above us. Tonight, I have lit a bonfire once more. We gather around its soft glow, warming ourselves, listening together to stories written not in ink, but in starlight. This evening, we will lift our eyes to the sky and allow ourselves to drift into the depths of the cosmos. We will journey backward through time, beyond centuries, beyond epochs, beyond even the 13.8 billion years we call the beginning of everything. Tonight, we step into the ultimate silence to explore one of humanity's most enduring questions. Before the Big Bang, what existed? Take a slow, deep breath. Let your chest rise, then gently fall. Feel the stillness spreading through every part of you. There is no need to wrestle with equations or the strict laws of physics. Let the warmth of the fire settle in. Let these words flow like a quiet stream of light, carrying your thoughts effortlessly through the darkness, easing you toward rest beneath the eternal glow of the stars. Tonight, I invite you to travel to the earliest moment imaginable, not thousands of years ago, not millions, but 13.8 billion years into the past. Welcome to the Big Bang, when the curtain rises. Together, we will witness the instant when space, time, and reality itself emerged from absolute nothingness. Prelude, the silence before dawn. Before our story begins, there is nothing. No matter, no energy, not even empty space, because space itself has not yet come into being. There is no flow of time, because time has no meaning here. The universe as we know it, its billions of galaxies and countless stars, exists only as pure potential, compressed into what scientists call a singularity. Imagine a point so small it cannot be measured, far smaller than an atom, yet holding all the mass and energy of everything that exists today. This point possesses infinite density and infinite temperature. It is a brilliant firewall where every physical law we understand, from Newton's gravity to Maxwell's equations, simply breaks down. Here, human knowledge reaches its edge, and even our most advanced mathematics begins to falter. In mathematics, a singularity is a place where values grow without limit, where familiar rules no longer apply. In cosmology, it marks a moment in the distant past when the entire universe was compressed into a region of zero volume. Let us unfold this idea gently. Infinite density means that the matter of more than 100 billion galaxies, each filled with hundreds of billions of stars, is squeezed into a point with no size at all. Infinite temperature means energy beyond anything even the fiercest stellar core could produce. Infinite curvature of space-time means the very fabric of reality bends so severely that space and time lose their usual meaning. Yet we must tread carefully. In physics, the appearance of infinity is often a warning, a signal that a theory has been stretched beyond where it can truly speak. A singularity may not be a physical object or location, but a boundary of understanding. It marks the point where general relativity, our finest description of the large and massive, can no longer guide us. Humanity's encounter with the idea of the singularity began just over a century ago. In 1922, Russian physicist Alexander Friedmann made a daring leap. Working from Einstein's equations, he proposed that the universe might be expanding, challenging the prevailing belief in a static cosmos. From this came a profound question. If the universe is expanding now, did it begin from a singular point? In 1931, Belgian physicist and priest Georges Lemaitre took the idea further. He proposed that the universe began as a primeval atom. If we rewind the cosmic film, he argued, all matter and energy converge to a single origin where space and time themselves are born. By 1959, physicist Lev Landau had formalized the problem of the singularity. In the 1960s, researchers Belinsky, Kalatnikov, and Lifshitz, known as the BKL group, studied Einstein's equations near this extreme boundary. They found that singularities were not rare oddities, but an unavoidable feature of cosmological models based on general relativity. The decisive moment arrived in 1970, when Stephen Hawking and Roger Penrose published their singularity theorems. They demonstrated mathematically that, under realistic conditions, a singularity at the beginning of the universe is inevitable if general relativity alone is used. With this, the Big Bang became firmly established as the standard model of cosmic origins. But the singularity is more than a clue to the past. It is a window into the deepest structure of reality. First, it is a scar of creation, reminding us that our understanding remains incomplete. At the singularity, the two great pillars of modern physics, general relativity and quantum mechanics, collide. One governs the immense, the other the infinitesimal. Here, the universe is both unimaginably large and impossibly small, and our equations dissolve into contradiction. Second, it drives the search for a theory of everything. To resolve the singularity, physicists seek a theory of quantum gravity, whether through string theory or loop quantum gravity. Such a framework is expected to remove infinities, replace them with finite values, and perhaps allow us to glimpse what truly lay beyond the Big Bang's fiery veil. Third, it reshapes the meaning of beginnings. If time and space themselves emerged at the singularity, then the question, what came before, loses its meaning. It is like asking what lies north of the North Pole. Once there, all directions lead south. In this view, the universe begins complete, without a classical before. Though the singularity lies at the heart of the traditional Big Bang model, many scientists now seek alternatives. One such idea is the no-boundary proposal by Stephen Hawking and James Hartley. By treating time as a special, primordial dimension, they suggest the universe has no sharp beginning, much like the surface of a sphere, finite yet without an edge or starting point. Another approach, rooted in loop quantum gravity, proposes that space itself is made of discrete units. When the universe contracts to an extreme density, a quantum repulsive force arises, preventing infinite collapse and triggering a big bounce. In this vision, the Big Bang is not a beginning from nothing, but the continuation of a universe that once existed before. The moment of origin, when the cosmic clock began to tick. Approximately 13.787 plus or minus 0.02 billion years ago, the greatest event in all of history quietly began. It is important to remember that the Big Bang was not an explosion in space, like a bomb detonating outward. There was no space yet to explode into. Instead, it was space itself that began to expand. From an infinitesimal singularity, space unfolded, carrying with it an immense surge of matter and energy, the first breath of the cosmos. The Planck epoch, ultimate unity, 10 to the power of minus 43 seconds. The earliest chapter of this story spans from time 0 to 10 to the power of minus 43 seconds, a fleeting interval known as the Planck epoch. In this incomprehensibly brief moment, all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single, elegant superforce. The universe at this instant resembled a perfect crystal, absolute simplicity, flawless symmetry, and complete unity. It was a state of purity that modern physics can describe only in fragments, at the very edge of understanding. Inflation, the great leap, 10 to the power of minus 36 to 10 to the power of minus 32 seconds. Then, almost instantly, something extraordinary occurred. The universe entered a phase known as inflation. Driven by an invisible energy field, the inflaton field, space expanded at a rate faster than the speed of light itself. In less than a trillionth of a second, the universe grew from a size far smaller than an atom to something comparable to a baseball. This sudden expansion smoothed and stretched the fabric of space-time, erasing irregularities and ensuring that the universe would appear nearly identical in all directions. Inflation solved two of cosmology's deepest puzzles, the flatness problem and the horizon problem. Even more quietly, it amplified tiny quantum fluctuations, minute ripples in energy, into vast cosmic seeds. From these seeds, galaxies, clusters, and the grand architecture of the universe would one day emerge. The silent battle, matter and antimatter. When inflation ended, its stored energy was released in a process known as reheating, flooding the universe with an intensely hot sea of particles. In accordance with Einstein's equation, E equals mc squared, energy transformed into matter. But nature presented a profound dilemma. Every particle of matter was created alongside a mirror counterpart, antimatter. Electrons appeared with positrons, protons with antiprotons. When matter met antimatter, both vanished in flashes of pure energy. The early universe became a relentless battlefield. Trillions upon trillions of particles annihilated one another every second. Yet, for reasons still not fully understood, a phenomenon scientists call baryogenesis, a tiny imbalance emerged. For every billion particles of antimatter destroyed, one extra particle of matter remained. Everything you see, the stars above, the earth beneath your feet, and your own existence, comes from that single surviving fragment. We are here because of an asymmetry so small it defies intuition. The quark soup and the birth of nuclei. As the universe reached an age of about 1 million seconds, it continued to cool. Temperatures, though still in the trillions of degrees, dropped enough for quarks, the fundamental building blocks of matter, to bind together in groups of three, forming protons and neutrons. At this stage, the universe resembled a dense, boiling cosmic soup. Then, between 3 and 20 minutes after the Big Bang, another crucial milestone arrived. Big Bang nucleosynthesis. Protons and neutrons collided and fused, forming the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. By the end of this brief window, roughly 25% of the universe's mass had become helium, a figure that modern astronomy continues to confirm with remarkable precision. The first light, cosmic microwave background. Even with atomic nuclei in place, the universe remained dark. For nearly 380,000 years, it existed as a hot, opaque plasma. Free electrons scattered photons endlessly, preventing light from traveling any meaningful distance. The cosmos was shrouded in a luminous fog. Then came a quiet turning point. As temperatures fell to around 3,000 Kelvin, electrons slowed enough to bind with nuclei, forming the first neutral atoms. This moment, known as recombination, changed everything. The fog lifted. Light was finally free to move across space. That ancient glow still surrounds us today, stretched by billions of years of cosmic expansion into what we now observe as the cosmic microwave background. The universe's earliest photograph, preserving the faint echoes of creation itself. The legacy of the discoverers. The Big Bang is not merely a theoretical construct. It is supported by enduring evidence. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, revealing that space itself is expanding. In 1964, Arno Penzias and Robert Wilson accidentally detected a persistent radio hiss while calibrating an antenna. That faint noise turned out to be the residual echo of the Big Bang itself. Even the name Big Bang carries irony. It was coined in 1949 by astronomer Fred Hoyle during a BBC broadcast intended as a dismissive remark. Hoyle opposed the theory, yet the phrase endured. becoming the name of the most successful model humanity has ever built to describe the origin of the universe. As the brilliant light of the cosmic dawn, the Big Bang, slowly fades behind the veil of history, we will not rush to gaze at blazing stars. Instead, we choose to listen for the faintest murmurs, the quiet whispers hidden deep within the shadows of creation. Welcome to Whispers from the Shadows, questions about something before the Big Bang. Tonight, we will decipher the oldest messages ever delivered to humanity, from delicate ripples in the cosmic microwave background to vast cosmic structures that challenge the limits of logic itself. Take a slow, gentle breath and allow this journey to carry you softly into sleep, cradled in the heart of eternity. Messenger from the Void, the cosmic microwave background. Our story truly begins on a warm summer day in 1964 in New Jersey. Picture two scientists, Arno Penzias and Robert Wilson, standing beside a massive horn-shaped antenna at Bell Laboratories. They were not searching for the origin of the universe. They were simply attempting to measure radio signals from space. Yet no matter where they pointed the antenna, no matter how carefully they cleaned it, dust, static, even pigeon droppings, a strange, persistent hiss remained. It was not interference from New York City. It was not faulty equipment. That quiet, stubborn noise was the cosmic microwave background, the lingering echo of the Big Bang itself, an ancient whisper that had traveled for nearly 14 billion years before reaching their ears. The blueprint of a baby universe. According to the Big Bang model, for the first 380,000 years, the universe existed as a dense, blisteringly hot sea of plasma. Free electrons moved endlessly, scattering photons at every turn, preventing light from traveling any meaningful distance. The universe was opaque, like a fog so thick that nothing could be seen through it. Then came a silent turning point known as recombination. As the universe cooled to around 3,000 Kelvin, electrons slowed and bonded with atomic nuclei, forming the first neutral atoms. In that moment, the fog lifted. Light, for the first time in cosmic history, was free to travel unimpeded across space. That ancient light still surrounds us today. Stretched by the expansion of the universe, its wavelengths have shifted into microwaves. When we observe the CMB, we are looking at the universe's infant photograph, a snapshot taken at the exact moment the cosmos became transparent. Tiny scars on smooth skin. At first glance, the cosmic microwave background appears perfectly uniform. But when satellites such as COBE, WMAP, and Planck examined it with exquisite precision, they revealed minute temperature variations, differences of only 1 part in 100,000. These faint blue and red speckles are not random noise. They are the primordial seeds of structure. Slightly cooler regions, areas of marginally higher density, became the gathering points where gravity would slowly assemble galaxies, stars, and eventually, us. Yet the CMB reveals something unsettling as well. It is almost too perfect. Its uniformity borders on the absurd. The horizon paradox, when uniformity becomes a mystery. Let your thoughts drift across this ocean of microwaves and consider the horizon problem. When astronomers measure the CMB in one direction, they record a temperature of 2.725 Kelvin. When they look in the opposite direction, billions of light years away, they find precisely the same temperature. This should not be possible. Even light, the fastest traveler in the universe, has not had enough time since the beginning to cross that immense distance and equalize conditions. It is like placing 2 cups of coffee on opposite sides of a continent and discovering that they share the exact same temperature, down to a fraction of a degree, without any heat ever passing between them. This suggests that before the Big Bang, or in its earliest moments, those distant regions were once close enough to exchange information. The universe may not have emerged from absolute disorder, but from a system that already possessed an underlying coherence. Cosmic inflation, a leap that erases memory. To resolve this paradox, physicist Alan Guth proposed the theory of cosmic inflation in 1979. He suggested that around 10 to the power of minus 36 seconds after the Big Bang, an invisible energy field caused space itself to expand at a rate faster than light. In an unimaginably brief instant, the universe grew from a size smaller than an atom to something comparable to a baseball. Inflation smoothed out all irregularities in space-time, explaining why the universe appears nearly flat and uniform today. But inflation came at a cost. It erased nearly all information about what existed before. The universe was born with an empty memory, yet inflation could not erase everything. Tiny quantum fluctuations, minute oscillations at the smallest scales, were stretched and frozen into the fabric of space. These are the faint imprints we now observe in the CMB, quantum whispers from an era that may predate inflation itself. The birth of inflation theory. The story of inflation truly took shape one December night in 1979, when Alan Guth was wrestling with equations involving magnetic monopoles, hypothetical particles predicted by theory but never observed. Suddenly, insight struck. If the universe had undergone a brief but violent expansion at its birth, those problematic relics would have been diluted away. Guth famously wrote two words in his notebook: spectacular realization. Borrowing a term from economics, he called this process inflation. Space, like prices in an inflating economy, expanded at an extraordinary rate. According to his calculations, the universe expanded by at least 10 to the power of 26 times in a fraction of a trillionth of a second. This expansion exceeded the speed of light because it was not matter moving through space, it was space itself stretching. Around the same time, Alexei Starobinsky in the Soviet Union independently proposed a similar idea based on quantum gravity effects. Later, refinements by Andre Linde, Andreas Albrecht, and Paul Steinhardt resolved early issues, leading to what became known as new inflation and later chaotic inflation. Linde's work opened the door to the idea of a multiverse where inflation occurs repeatedly, spawning countless universes, each with its own Big Bang, the inflaton field. At the heart of inflation lies a hypothetical entity known as the inflaton field. Imagine it as a spring compressed to its absolute limit. When released, it unleashes an enormous amount of energy, forcing space to expand violently before settling into a calmer state. Whether this field truly exists remains an open question, but its fingerprints may still be etched into the oldest light we can observe. In quantum physics, this condition is known as a false vacuum. It is an unstable state, filled with enormous energy, and marked by one strange property: negative pressure. According to Einstein's theory of relativity, negative pressure does not pull matter together. It pushes space apart. Quietly but relentlessly, it takes control of the universe's expansion, stretching the fabric of space-time faster and faster, as if the cosmos itself were being gently, but irresistibly, unfolded. Inflation in this sense is the ultimate free lunch. Every galaxy, every star, every atom of mass and energy we see today was born from tiny fluctuations in the inflaton field during this brief, violent episode. When inflation finally came to an end, the inflaton field decayed, releasing all its stored energy at once. Space was flooded with a scorching sea of primordial particles. This moment is known as reheating, and it marks what we call the hot Big Bang. Inflation is not merely an elegant idea. It is the missing key that allows us to fully understand the cosmic expansion Edwin Hubble uncovered in 1929. First, it explains why the universe is so astonishingly uniform and flat. Inflation stretched space so dramatically that any original curvature was smoothed away, much like the surface of a small balloon appears flat when inflated to the size of the Earth. At the same time, It allowed distant regions of space to once communicate and share information, settling into the same temperature before being flung apart forever. Second, inflation explains the birth of galaxies. At the quantum level, Heisenberg's uncertainty principle tells us that energy is never perfectly still. Tiny fluctuations constantly ripple through space. Without inflation, these fluctuations would remain microscopic and meaningless. But inflation magnified them, freezing these delicate quantum tremors into vast cosmic imprints, regions just slightly denser than their surroundings. Over billions of years, gravity patiently gathered matter there, shaping stars, galaxies, and ultimately ourselves. Third, inflation offers a glimpse into the future. By studying it, scientists can compare this ancient burst of expansion with the accelerated expansion we observe today, driven by dark energy. Although inflation operated at energy levels trillions of times greater, both phenomena share a common thread: negative pressure and the expansion of space itself. To explore inflation is to listen to how the universe breathes and to sense how it quietly steers its own fate. The Ghosts of Roger Penrose, an eternal loop. While most scientists believe inflation erased all traces of what came before, Sir Roger Penrose, a Nobel Prize-winning physicist, proposed a far more daring vision through his theory of conformal cyclic cosmology, or CCC. Penrose suggests that the Big Bang was not a beginning, but a transition, a bridge between cosmic aeons. In his view, when an old universe expands to its ultimate limit, matter gradually decays until only radiation remains. In this final ghostly state, time and scale lose their meaning, becoming mathematically indistinguishable from the conditions of a new Big Bang. Scars from ancient black holes. Penrose has even claimed to see hints of this past universe in data from the Planck satellite. Faint, concentric circles embedded in the cosmic microwave background. He interprets these rings as energetic scars, echoes left behind by collisions between supermassive black holes in a universe that existed before ours. Many scientists remain skeptical, yet the idea opens a haunting possibility that the warmth we observe today may include embers from a long-dead cosmos, a universe that burned brightly before our own 13.8 billion years ever began. Leviathans in the darkness, structures that defy time. When we step back and observe the universe on its largest scales, we see an immense lattice known as the cosmic web. Standard cosmology predicts that matter should be fairly evenly distributed, and that no structure should exceed about 1 billion light-years in size. Then came a surprise. In 2024, astronomers reported the discovery of the Big Ring, a colossal structure spanning up to 1.3 billion light-years in diameter, with a circumference of nearly 4 billion light-years. Nearby lies another giant, the Giant Arc, stretching an astonishing 3.3 billion light-years across space. Why do these discoveries matter? First, they challenge the limits of physics. These structures appear too vast to have formed through ordinary gravitational growth within 13.8 billion years. It is like discovering a vast stone fortress where only small villages should exist. Second, they hint at something pre-cosmic. Researchers such as Alexia Lopez have suggested that these leviathans may be remnants of unfamiliar early universe physics, or perhaps subtle fingerprints of a universe that existed before the Big Bang itself. Third, there is the maturity problem. The James Webb Space Telescope has revealed galaxies that appear far too developed for their supposed age. Some studies have even questioned whether the universe might be older than we think, proposing ages as high as 26.7 billion years to give these giants enough time to grow. When nothingness begins to speak. Now, let us imagine the state before the Big Bang not as empty darkness, but as a restless quantum ocean. According to the uncertainty principle, energy can never be exactly zero. Even in what we call nothing, virtual particles continuously flicker into existence and vanish again. In this view, the pre-Big Bang universe may have been a vast false vacuum, laden with immense stored energy. The Big Bang, then, was not creation from nothing, but a rupture, a moment when a region of this vacuum collapsed, releasing its hidden power and giving birth to our cosmos. Here, the universe becomes the ultimate free lunch, the positive energy of matter perfectly balanced by the negative energy of gravity, leaving the total energy of existence at precisely zero. Perhaps before the Big Bang, there was not silence, but a profound stillness, not the quiet of death, but the pause of anticipation. Like a flawless symphony resting on the page, waiting for the first note to be played in the dark. Night travelers, let us continue our journey with redefining nothingness. A quiet meditation on the idea that emptiness does not truly mean nothing at all. We often imagine nothingness as an ending, a cold, tasteless void where all meaning dissolves. Yet, under the calm gaze of modern physics, nothingness reveals itself as a vibrant stage, a hidden reservoir of possibility from which the eternal radiance of the stars has quietly emerged. Ancient fears and Aristotle's veil. Our story begins thousands of years ago in the contemplative minds of ancient philosophers. To Aristotle, the idea of absolute emptiness was not just wrong, it was unthinkable. It violated the harmony of nature itself. He proposed the principle of horror vacui. Nature, he believed, abhors a vacuum. According to Aristotle, every space must be filled by air, by liquid, or by some unseen substance, because motion itself requires matter. An empty space, in his view, could not exist. For centuries, this belief shaped humanity's understanding of reality. Nothingness came to mean the absolute absence of existence. No properties, no laws, no potential. Even when, in the 17th century, Torricelli and Pascal demonstrated that airless regions could be created, the vacuum was still thought of as a passive container, an empty vessel waiting patiently for matter to arrive. Isaac Newton would later describe space as absolute, eternal, fixed, and indifferent to whatever occupied it. But now, take a slow breath. Because as we step into the world of the infinitesimal, the quantum realm, the illusion of a silent vacuum begins to unravel. The silent pulse of the quantum vacuum. Imagine gazing into a region of space stripped of everything. No atoms, no light, no warmth. Classical physics would tell us that such a place contains zero energy. Yet Werner Heisenberg, one of the architects of quantum mechanics, revealed a deeply unsettling truth through the uncertainty principle. This principle tells us that energy and time cannot both be known with perfect precision. Try to force energy to be exactly zero for even a fleeting moment, and the universe resists. At the subatomic scale, the vacuum is not smooth or still. It quivers. It trembles. This restless activity is known as zero-point energy. Even in its lowest possible state, the vacuum carries an unending quantum murmur. From this invisible sea, pairs of virtual particles and antiparticles constantly flicker into existence, dance briefly, and vanish again, borrowing energy from the universe before returning it in an instant. The vacuum, then, is not emptiness. It is a living physical entity, quietly overflowing with potential. Antimatter and Paul Dirac's prophecy. Within this turbulent quantum ocean exists a strange mirror of our world, antimatter. In 1928, physicist Paul Dirac was attempting to reconcile quantum mechanics with Einstein's relativity when his equations led him to an unexpected conclusion. Just as the square root of 4 has both a positive and a negative solution, Dirac's mathematics implied that the electron must have a counterpart, identical in mass, but opposite in charge. With remarkable courage, Dirac predicted the existence of the positron. Only 4 years later, in 1932, Carl Anderson detected it in cosmic rays, confirming that reality possesses a perfectly symmetrical shadow. Antimatter is not a science fiction fantasy. It behaves exactly like ordinary matter, except for its reversed electric charge and quantum properties. And when matter meets antimatter, the result is annihilation. Both disappear, releasing their entire mass as energy in the form of light, just as Einstein's equation E equals mc squared foretells. The presence of antimatter within the vacuum stands as one of the clearest signs that nothing is, in fact, a delicate balance between existence and obliteration. The Casimir effect, when nothingness creates force. You might wonder, in the quiet of the night, if these particles are only virtual, if they vanish so quickly, do they truly matter? The answer arrives in the form of a subtle and almost poetic phenomenon known as the Casimir effect. In 1948, Dutch physicist Hendrik Casimir proposed a startling idea. Place two ultra-thin, uncharged metal plates parallel to one another, extremely close together, inside a perfect vacuum, and they will be drawn toward each other by an invisible force. Why? Because the vacuum is alive with quantum vibrations of every possible wavelength. Between the two plates, space becomes constrained. Only certain wavelengths are allowed to exist there. Outside the plates, however, all wavelengths remain free, and their collective pressure gently but inexorably pushes the plates together. This effect has been measured and confirmed with extraordinary precision. It proves that a vacuum can exert force, pressure, and influence. Nothingness is not inert. It has structure. It has weight. It can bend the fabric of space-time itself. The Casimir effect stands as quiet, undeniable evidence of the immense power concealed within what we so casually call emptiness. What then is the result? The number of virtual particles outside the plates is greater than the number inside. From this imbalance arises a very real pressure, gently but relentlessly pushing the two metal plates toward each other. This is the Casimir effect, a tangible force born not from matter, but from nothingness itself. The Casimir effect is far more than a curious laboratory trick. It stands as one of the quiet pillars of modern physics for several profound reasons. First, it is direct experimental proof of vacuum energy. Repeated and refined measurements have confirmed it with remarkable precision. The vacuum is not empty. It possesses intrinsic energy. This strengthens the very foundation of quantum field theory, reminding us that all fundamental particles are, at their core, vibrations of invisible energy fields that permeate space. Second, it presents a serious challenge and opportunity in nanotechnology. As we build machines on ever smaller scales, components are placed dangerously close together. At such distances, the Casimir force becomes significant. It can cause microscopic parts to cling together, leading to failure. Learning how to understand and control this force is essential if humanity is to move confidently into the age of nanomachines and micro-robotics. And third, perhaps most captivating of all, it offers a key to the dream of time travel. To construct a stable wormhole or a time machine, physics demands something extraordinary, exotic matter carrying negative energy. Such energy counteracts gravity, preventing space-time tunnels from collapsing under their own weight. The Casimir effect provides living proof that negative energy is not mere fantasy. By suppressing long wavelengths between two metal plates, we create a region whose energy density is lower than that of ordinary empty space. If we define the vacuum as zero, then the space between the plates becomes a genuine negative energy region. In this quiet way, the Casimir effect transforms wormholes from pure science fiction into a topic of serious scientific contemplation. The universe, the greatest free lunch. If the vacuum holds energy and if it can generate force, a deeper question naturally follows. Could it create an entire universe? This brings us to the elegant idea of a zero-energy universe. Consider all the brilliance you see: galaxies, stars, planets, and even yourself. All of this matter carries enormous positive energy, yet gravity, which binds it all together, carries negative energy. Cosmologists, including Alan Guth, have recognized a delicate and beautiful balance. The total positive energy of matter may be perfectly canceled by the negative energy of gravity. If this is true, then the total energy of the universe is exactly zero. In such a universe, no external energy is required for creation. Our cosmos may simply be a vast quantum fluctuation, rising spontaneously out of nothingness. It is the ultimate free lunch, existence emerging without violating a single conservation law. The Casimir effect, small though it may seem, is one of the most compelling pieces of evidence that primordial nothingness can bend space-time and give rise to everything. False vacuum and the inflationary burst. But one question still lingers in the dark. Why did nothingness choose to erupt 13.8 billion years ago? The answer may lie in a subtle state known as the false vacuum. Imagine a ball resting on a high plateau beside a deep valley. It appears stable, yet it holds immense potential energy. A single disturbance could send it cascading downward. Before the Big Bang, the universe may have existed in such a false vacuum state, governed by an entity known as the inflaton field. Through a random quantum event, something called tunneling, this field slipped into a lower energy state. Einstein's equations tell us that a high-energy vacuum possesses a strange and powerful property: negative pressure. Rather than pulling inward, it pushes outward. This pressure drove space itself to expand at a rate faster than light. This was the era of cosmic inflation, the moment when a tiny seed of existence, born from nothingness, expanded to the size of a baseball in a fraction of a trillionth of a second, laying the groundwork for everything we know. Baryogenesis. Why are we here? Yet nothingness, having given birth to everything, nearly erased it all at once. In the searing furnace of the early universe, matter and antimatter were created in almost perfect symmetry. Had this balance been exact, every particle would have found its mirror opposite. They would have annihilated each other completely, leaving behind only a faint afterglow and no life. But a quiet miracle occurred. Through a process known as baryogenesis, tied to subtle violations of nature's symmetries, a tiny imbalance arose. For every billion pairs of matter and antimatter that vanished, one lonely particle of matter remained. That single survivor made all the difference. You and I, mountain ranges and distant galaxies, are the fortunate remnants of that ancient conflict. We exist because nothingness was not perfectly symmetrical. Nothingness, then, is not the death of matter. It is the silence before a symphony begins. Every atom in your body still carries the faint heartbeat of quantum oscillations that first stirred 13.8 billion years ago, when emptiness learned how to speak. Welcome to the Blueprints for Before We Begin. Let my voice become your quiet companion, guiding you gently into a dreamlike realm, where mathematical equations soften into poetry, and the laws of physics pulse like the slow, steady rhythm of eternity. The boundary of collapse and the Planck era. Our story begins at the very edge of comprehension, where familiar laws quietly dissolve. According to the standard cosmological model, if we rewind the film of the universe far enough, all matter and energy converge into a single point known as the singularity. Here, density and temperature approach infinity, and the fabric of space-time twists beyond imagination. Yet physicists have learned to treat infinity not as an answer, but as a warning, a signal that our equations have reached the end of their usefulness. The furthest boundary modern physics can meaningfully describe is the Planck era, an interval so brief it defies intuition. Just 10 to the power of minus 43 seconds after the beginning. At this scale, space and time are no longer smooth and continuous. they fragment into a restless, turbulent structure, often described as quantum foam. To speak meaningfully of what existed before this moment, we require an entirely new blueprint, a language capable of uniting the vast geometry of relativity with the delicate uncertainty of quantum mechanics. The blueprint from nothingness, an emergence from the quantum vacuum. Now imagine the state before the Big Bang not as empty darkness, but as a turbulent quantum ocean. According to Heisenberg's uncertainty principle, energy can never be perfectly still. Absolute zero is forbidden. In this blueprint, nothingness is not silent, it is alive. Vacuum volatility. What we call the vacuum is a shimmering sea of ghost-like energy, where virtual particles and antiparticles continuously appear and vanish, too fleeting to observe directly, yet undeniably real. Quantum tunneling. Physicist Alexander Vilenkin proposed that our universe may have emerged through a process known as quantum tunneling, a probabilistic leap from nothingness into existence, overcoming barriers that classical physics deems impassable. The Great Free Lunch. Mathematical models suggest something astonishing. The total energy of the universe may be exactly zero. The immense positive energy of matter is perfectly balanced by the negative energy of gravity. In such a universe, creation requires no external input. Existence arises naturally, without violating any conservation law. The eternal inflation blueprint, bubbles in a boundless ocean. If the first blueprint speaks of a singular beginning, eternal inflation reveals a far grander landscape, the multiverse. The inflaton field. Scientists hypothesize a field stretched like a tightly compressed spring, saturated with energy. False vacuum. Before our Big Bang, reality may have existed in a high-energy state known as a false vacuum. Its intense negative pressure forced space itself to expand faster than light, not as motion through space, but as space becoming more space. Endless branching. In most regions, inflation never stops, but in rare pockets, the inflaton field decays, releasing heat and matter in an event called reheating. Our Big Bang may simply mark the moment one such bubble cooled. Our universe, born quietly within a vast, ever-expanding ocean. The Big Bounce blueprint, the breath of the universe. One blueprint challenges the idea of a true beginning altogether. The Big Bounce, inspired by loop quantum gravity. The pixel structure of space. Rather than a smooth continuum, space-time may be composed of discrete units, atoms of space, at the Planck scale. Quantum repulsion. As a previous universe collapsed inward, density rose to a quantum limit. At that point, gravity reversed its role, becoming strongly repulsive rather than attractive. The eternal loop. Instead of collapsing into a singularity, the universe rebounded, bouncing outward into a new expansion. In this vision, before the Big Bang was not nothingness, but a universe much like ours, slowly contracting. The membrane collision design. Echoes from higher dimensions. Drawing from string theory and M theory, physicists such as Paul Steinhardt proposed the ekpyrotic model. The membrane universe. Our three-dimensional cosmos may be a thin membrane, called a brane, floating within a higher dimensional space known as the bulk. The gentle collision. Before the Big Bang, two such membranes drifted parallel to one another, separated by a minute distance. Over immense time, gravity drew them closer. The birth of fire. The Big Bang was not a singularity, but the moment these membranes touched, their collision transformed motion into heat and matter, giving rise to a flat, uniform universe without the need for inflation. Penrose's conformal cyclic cosmology, a universe without end. Sir Roger Penrose, Nobel Prize-winning physicist, offered a vision rich with mathematical elegance and philosophical depth. Conformal cyclic cosmology, CCC. The disappearance of mass. In the far future, stars fade, black holes evaporate, and only massless particles remain. The loss of scale. For photons, time and distance lose meaning. An infinitely cold, dilute universe becomes mathematically equivalent to an infinitely hot, dense beginning. Scars in the cosmic light. Penrose suggested that faint concentric patterns in the cosmic microwave background may be echoes of black hole collisions from previous aeons. In this view, our Big Bang is not a beginning, but a transition in an eternal sequence. Chapter 7. The Mini-Bang's Blueprint. A recent and provocative hypothesis from Richard Liu, 2025, challenges the idea of a single cosmic explosion. Temporary singularities. Instead of one Big Bang, the universe may have emerged from countless transient mini-bangs, brief and localized bursts unfolding over time. The origin of dark matter. Each event injects matter and energy uniformly, potentially explaining dark matter and dark energy without invoking unknown particles. In this blueprint, the moment we call the Big Bang was preceded by a long series of silent, preparatory cosmic events. Night travelers, as we stand at the edge of what we know and gaze upon these blueprints of before, a gentle truth reveals itself. The universe is not a random accident. It is a vast symphony, patiently composing its own movements. Whether born from a bounce, a collision between dimensions, or a fluctuation in the quantum ocean, every atom within you carries the echo of those ancient mysteries. You are not a stranger in the void. You are a verse within an ongoing poem, matter briefly aware of itself. Now, allow thoughts of space-time and eternal cycles to soften and fade. Let them dissolve into the quiet mist of dreams. Everything moves in its own grand rhythm, and so do you. Let your heartbeat fall into harmony with the stars. Close your eyes. There is nothing left to seek, only the calm glow of the Milky Way, gently holding you in its light. Night travelers, come and sit with us as we continue our journey in a perspective from early chemistry and physics. Tonight, we will not look at the universe only as a vast physical structure. Instead, we will illuminate it through the careful eyes of a chemist and the quiet intuition of the earliest physicists. Together, we will ask a gentle but profound question. What is the true material of nothingness, and which laws guided creation before the first heartbeat of time? Take a slow, deep breath. Feel the boundless embrace of space around you, and allow this journey to carry you softly towards sleep, deep within the calm center of eternity. The chemist's search for origins, the menu of the universe. In this stillness, imagine yourself as a cosmic chemist standing before an immense, softly boiling cauldron. You do not begin with the complex molecules of life, but with the simplest ingredients imaginable. To understand what existed before the Big Bang, chemists did something remarkable. They read the universe's cookbook backward, fragments from the primordial forge. Modern science tells us that everything you are made of, the iron flowing in your blood, the calcium strengthening your bones, even the air filling your lungs, was forged in stars. Yet when we travel back 13.8 billion years, chemists uncover a striking simplicity. The early universe contained only three elements: hydrogen, helium, and a faint trace of lithium. This brief but critical phase is known as Big Bang nucleosynthesis. Between 3 and 20 minutes after the universe began expanding, the cosmos functioned as a vast nuclear furnace. By observing that the most ancient regions of space still contain roughly 75% hydrogen and 25% helium, scientists confirmed the accuracy of this model. But this discovery raised a deeper question. If the universe began with such a simple menu, what existed before elements themselves were possible? The era of quarks and gluons. Traveling further back to temperatures of trillions of degrees, even atomic nuclei could not survive. Chemistry dissolves into something more primitive. At this stage, the universe existed as an unfamiliar substance known as quark-gluon plasma. Instead of atoms, Reality was filled with a dense, flowing mixture of quarks, the building blocks of protons and neutrons, and gluons, the particles that bind them together. Experiments at particle accelerators, such as RHIC and the Large Hadron Collider, have recreated this state and revealed something unexpected. The early universe behaved not like a gas, but like an almost perfect liquid. From a chemical perspective, this suggests that before recognizable matter emerged, the universe existed as a smooth, dynamic, and remarkably uniform energy fluid. Matter still learning how to become solid. Physicists and the pursuit of ultimate unity. Now let your thoughts drift beyond particles and toward the invisible forces that govern them. Early physicists did not see the universe as a collection of objects, but as a web of interactions, the Great Unification Era. Today, we recognize four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Yet as we approach the earliest moments of the universe, physicists believe these forces were once unified. Between roughly 10 to the power of minus 43 and 10 to the power of minus 36 seconds after the beginning, an era known as the Grand Unification Epoch, three of these forces merged into a single superforce. The universe at this moment resembled a flawless crystal, perfectly symmetrical, where distinctions between particles and forces had not yet formed. This hints that the pre-Big Bang state may have been one of complete unity, an undivided whole prior to separation and structure. The Planck wall, where mathematics falls silent. As we approach the Planck time, an invisible boundary appears. Here, the universe was unimaginably small, far tinier than any subatomic particle. At this scale, general relativity and quantum mechanics collide, producing results that no longer make sense. The singularity is not a physical object. It is an admission that our equations can no longer speak. Early physicists suspected that before the Big Bang, space and time as we understand them may not have existed at all, or may have been woven from discrete units too small for us to observe. The alchemy of nothingness, when emptiness is not empty. Now take another slow breath and imagine emptiness itself. To a quantum physicist, nothingness is not silent. It is alive with possibility, vacuum oscillations, and virtual particles. According to Heisenberg's uncertainty principle, energy can never be perfectly still. Even in a perfect vacuum, pairs of virtual particles and antiparticles continuously appear and vanish. This restless activity suggests that nothing is, in fact, a sea of potential. Physicists speculate that the state before the Big Bang may have been such a quantum ocean, awaiting a disturbance large enough to give rise to an entire universe. The Casimir effect. The power of exclusion. When two metal plates are placed extremely close together in a vacuum, they are gently pushed toward one another by the pressure of virtual particles. This measurable force proves that empty space carries energy. And if nothingness can create force, then creating matter is not beyond imagination. The universe as the ultimate free lunch. From this perspective, the universe itself may be a perfect balance. The positive energy of matter, galaxies, stars, and life, is offset by the negative energy of gravity. The total energy may be exactly zero. This allows the universe to arise from a quantum fluctuation without borrowing anything from outside itself. Bold blueprints for before the beginning. As physics stretches beyond the singularity, several profound scenarios emerge. The Big Bounce. In loop quantum gravity, the universe behaves like a breathing entity. A previous universe contracts until quantum repulsion halts the collapse and triggers a rebound. In this view, before our Big Bang was another universe, slowly exhaling into ours. The ekpyrotic model. In higher dimensional theories, our universe may be a thin membrane floating in a vast bulk. The Big Bang occurred when two such membranes gently collided, transforming motion into matter and heat. Eternal inflation and the multiverse. Imagine an endless ocean of expanding energy. Occasionally, calm regions form bubbles. Our universe is one such bubble. Before it, inflation continued endlessly, producing countless other beginnings. The complicity of fate, matter, mass, and meaning. Even at birth, the universe revealed delicate imbalances. Baryogenesis. Matter and antimatter should have formed equally. Yet a tiny asymmetry allowed one particle of matter to survive per billion annihilations. You are made of those survivors. Was this imbalance written into reality before time itself? The Higgs field. Around 10 to the power of minus 12 seconds after the beginning, particles gained mass through the Higgs field. Without this quiet transformation, atoms could never form, and neither could life. And so, night travelers, we see that chemistry and physics are not merely studying particles and forces. They are listening to the opening notes of a cosmic symphony. Whether born from a bounce, a collision between dimensions, or a fluctuation in a quantum sea, one truth remains. Every atom within you carries echoes from before time began. You are not a visitor in this universe. You are the universe, slowly awakening to understand itself. Now let these thoughts drift gently into the dark. The stars are still there, and so are you. While the ember of curiosity still glows quietly within us, one question continues to return, again and again, like a soft knock in the dark. Before the first light burst into existence, what was nothingness truly like? When we lift our eyes toward the brilliant night sky, time often feels like an unbroken river, flowing steadily from past to future. Yet if we were able to perform a great rewind on the cosmic film reel, everything would begin to contract. Distant galaxies would drift closer together. Space itself would shrink. Temperatures would rise to unimaginable extremes. Eventually, according to Einstein's general theory of relativity, this backward journey leads us to a singularity, a state of infinite density, infinite temperature, and zero volume. And here, at this point of absolute extremity, the physicist's nightmare begins. The elegant equations that describe the universe with such confidence suddenly collapse when confronted with the concept of infinity. The first paradox reveals itself as a trap of language. We ask what existed before the Big Bang. Yet if space and time themselves were born in that moment, then the word before loses its meaning. Stephen Hawking once compared this question to asking what lies north of the North Pole. Once you reach the pole, every direction points south. Our minds, shaped by cause and effect, struggle with this contradiction. Perhaps the Big Bang was not the beginning within time, but the beginning of time itself. And if there was no earlier moment to serve as a cause, what then ignited the universe? Did it simply emerge from nothingness? In classical philosophy, Aristotle defined nothingness as the absolute absence of existence. Modern science, however, offers a far more restless and provocative picture. When we examine the vacuum through the lens of quantum mechanics, emptiness dissolves. What we find instead is a quantum vacuum, restless and alive, seething like a dark, invisible sea of energy. According to Heisenberg's uncertainty principle, energy can never be perfectly still. Even in a so-called perfect vacuum, energy briefly borrows from nothingness, giving rise to pairs of virtual particles and antiparticles. They appear, exist for a fleeting instant, perform a silent dance, and annihilate one another, returning the borrowed energy as if nothing had happened. The clearest evidence of this hidden activity is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, they are gently pushed toward each other by the pressure of these virtual particles. Nothingness, it seems, is not silent at all. And this leads to a startling thought. If nothingness can generate force, could it also give rise to an entire universe? Alan Guth's idea of the ultimate free lunch suggests that the total energy of the universe may be exactly zero. The immense positive energy of matter, spread across billions of galaxies, is precisely balanced by the negative energy of gravity. If this balance holds, then our universe may simply be a colossal quantum fluctuation, emerging naturally from a vacuum state without violating any conservation laws. Yet even with this possibility, our understanding encounters a boundary. Science still stands before a wall known as Planck time, roughly 10 to the power of minus 43 seconds after the beginning. Beyond this threshold, we lack a unified theory capable of reconciling gravity with quantum mechanics. The singularity, then, may not be a physical object at all, but a scar, a sign that our mathematical language has reached its limits. It marks a frontier where knowledge hesitates and darkness temporarily prevails. Within that darkness, bold ideas take shape. Some, like Sir Roger Penrose, propose a cyclical universe where our Big Bang is merely the continuation of a previous cosmic era that expanded, faded, and gave birth to a new beginning. Penrose has even suggested that faint concentric patterns in the cosmic microwave background may be echoes of black hole collisions from an earlier universe. Others look to the ekpyrotic model, envisioning our universe as a three-dimensional membrane drifting within a higher dimensional space. In this view, the Big Bang was not an explosion, but a gentle contact between two such membranes in an eternal realm. There is also the theory of eternal inflation, which suggests that our universe is only a single bubble in an ever-expanding cosmic sea, endlessly spawning new universes. In this framework, what we call before the Big Bang is simply the timeless existence of a larger multiverse. These ideas challenge not only our calculations, but our intuition. Is the universe a singular miracle, a rare coincidence, or part of an endless rhythm of birth, decay, and renewal? Amid all this uncertainty, one delicate imbalance saved everything we know: baryogenesis. According to symmetry, matter and antimatter should have formed in equal amounts and annihilated completely, leaving behind only faint radiation. Yet, for reasons we still do not fully understand, nature favored matter by the smallest margin imaginable. For every billion pairs of matter and antimatter destroyed, a single particle of matter survived. You, I, the stars above us, all are built from these rare survivors. One cannot help but wonder, was this imperfection written into reality from the very beginning? We now live in a golden age of observation. Telescopes such as the James Webb Space Telescope peer deeper into the past than ever before, revealing galaxies that appear surprisingly mature for their age. Vast structures, like the colossal Big Ring stretching over 1 billion light-years, challenge established models and whisper that the universe may still be keeping its earliest secrets. Nothingness, then, is not a frozen void. It is a reservoir of possibility, a block of uncarved marble containing every universe that could ever exist. The Big Bang was simply the first stroke upon that stone. When faced with this mystery, fear gives way to reverence. Science may not yet penetrate the firewall of the beginning, but your very existence is proof of continuity. Every carbon atom in your body, every iron particle in your blood, forms an unbroken thread leading back to those primordial moments. You are not a stranger who wandered into this universe by accident. You are the universe awakening, using matter forged in the Big Bang to contemplate its own origins. Questions about what came before may never be fully answered, but it is precisely this uncertainty that gives human discovery its quiet, enduring beauty. Everything remains in motion. Space continues to expand, and nothingness still surrounds us, patient and vast. Take a slow breath. Let your heartbeat align with the distant rhythm of the stars. Within that deep silence lies the promise of yet another beginning. Are you still awake, night travelers? It would be a kindness if you were already drifting into sleep. But if you are still listening, let this soft firelight steady your thoughts. Allow these stories to flow like a gentle current, carrying your mind through the void as we turn our attention to the expansion of the universe, the eternal breath that shapes reality itself, the nature of infinity, how space breathes. We often imagine the universe as a vast static container, with stars and galaxies placed inside like ornaments. Science, however, reveals a far stranger truth. The universe is not still. It is expanding, quietly, relentlessly. Picture a loaf of raisin bread in the oven. The galaxies are the raisins, space is the dough. As the loaf expands, the raisins move farther apart. They are not traveling through the dough itself is growing. This is cosmic expansion. Galaxies are not simply moving through space. Space itself is stretching. It bends, it expands, it vibrates. With every passing second, the universe contains more space than it did before. The difference between reality and common imagination. When we hear about the expansion that followed the Big Bang, many of us instinctively picture a colossal explosion. A single point erupting outward, scattering matter into an empty, pre-existing space. It is a powerful image, but one that modern science has quietly and firmly set aside. The universe does not expand into anything. In everyday experience, when something grows, it must occupy space beyond itself. Yet the universe is not an object within a larger container. It is all that exists. There is no external space waiting beyond its borders. The expansion is not outward, but inwardly profound. Space-time itself is stretching, creating more of itself as it goes. The universe has no center and no edge. In an ordinary explosion, we can always trace debris back to a central origin. The Big Bang was nothing like that. It did not occur at one location within space. It happened everywhere at once. From any galaxy you choose to observe, all other galaxies appear to be moving away, creating the illusion that you are at the center. In truth, every point in the universe is equal. The universe expands from nothingness, and it expands toward nothingness. Faster than light does not break the rules of physics. At vast enough distances, galaxies are receding from us at speeds greater than the speed of light. This sounds alarming, but it violates no law. Einstein's limit applies to objects moving through space. Here, it is space itself that is expanding, carrying galaxies along like leaves on a widening river. Footsteps in the darkness. How we discovered the universe is expanding. The realization that space itself is breathing did not come easily. For centuries, even the greatest minds, including Isaac Newton and Albert Einstein, believed the universe was static and eternal. Einstein went so far as to add a term, the cosmological constant, to his equations to prevent cosmic collapse, later calling it his greatest mistake. The shift began quietly in the early 20th century. Astronomer Vesto Slipher noticed that light from distant nebulae was redshifted. Much like the lowering pitch of a train whistle as it moves away, light stretches as its source recedes, sliding toward the red end of the spectrum. In 1929, Edwin Hubble brought clarity to the mystery. By measuring both the distances to galaxies and their speeds of recession, he uncovered a simple yet astonishing relationship. The farther away a galaxy is, the faster it is moving away from us. This discovery, now known as Hubble's law, revealed that the universe was once more compact and has been expanding ever since. Then, in 1964, evidence arrived in the most gentle and unexpected form. Arno Penzias and Robert Wilson, using a radio antenna, detected a faint, persistent hum coming from every direction in the sky. This signal, later identified as the cosmic microwave background, is the lingering afterglow of the universe's earliest hot, luminous state, a quiet echo of its first great expansion. The eras of expansion, from inflation to dark energy. The universe has not expanded at a steady pace. Like a living being, it has known moments of violent breath and long periods of restraint. The inflation era. In the first instant, around 10 to the power of minus 32 seconds after the Big Bang, the universe underwent an extraordinary surge. Space expanded at a rate vastly exceeding the speed of light. In a fraction of a heartbeat, a region smaller than an atom grew to the size of a baseball. This inflation smoothed the fabric of space-time and ensured that the universe would appear remarkably uniform in every direction. The gravitational braking phase. Once inflation ended, gravity took hold. For billions of years, the mutual attraction of matter and dark matter slowed the expansion, allowing stars, galaxies, and clusters to take shape. Gravity acted as a cosmic brake, giving structure time to emerge. The dark energy revolution. Roughly 5 billion years ago, the story changed again. As matter became more diffuse, a mysterious influence known as dark energy began to dominate. Instead of slowing down, the expansion accelerated. Today, dark energy accounts for about 68% of the universe's total energy content, behaving like a gentle but relentless anti-gravity, pushing galaxies ever farther apart. Why the time before the beginning still matters. You may wonder why scientists concern themselves with what happened before the Big Bang, when the expansion itself is already so well described. The answer lies in the singularity, a point where density and temperature become infinite, and our physical laws lose their meaning. To understand what truly triggered expansion, we must peer beyond this mathematical breakdown. The way the universe expanded preserves priceless clues. During inflation, tiny quantum fluctuations, imperceptible disturbances at the smallest scales, were stretched across the cosmos, becoming the seeds of galaxies and cosmic structure. Their faint imprints remain visible today in the subtle patterns of the cosmic microwave background. By studying expansion, we are, in essence, rereading the universe's original blueprint. The state before the Big Bang may have been absolute silence, yet a silence filled with potential. The Big Bang was not the creation of everything, but the first decisive strike upon that potential stone, the opening note of a vast symphony, within which each of us is a single, quiet tone, still resonating through the dark. Take a deep breath. Let the silence settle gently into every cell of your body, and allow yourself to drift with me toward the farthest frontiers of reality. Tonight, we listen closely to the great breath of space itself, and we ask a quiet but profound question. How do we know the universe is breathing? In our everyday imagination, we often picture the universe as a vast, silent container, unchanging and eternal, where stars and galaxies are placed like ornaments in a box. Yet the universe revealed by science is far more alive, far more restless. It is not a static stage upon which events unfold. It is an active participant, constantly expanding from within. This expansion is not a violent scattering of galaxies through space, like fragments from an explosion. Instead, it is a slow and relentless increase in the distance between regions of the universe, not held together by gravity. Space itself is stretching. A gentle image may help. Imagine a loaf of raisin bread baking in an oven. The galaxies are the raisins. Space is the dough. As the bread rises, the raisins do not crawl away from one another. The dough itself expands, quietly pushing them apart. In much the same way, with each passing second, the universe contains more space than it did a moment before. Humanity's realization of this cosmic breath was not immediate. It was an intellectual journey that required the shattering of a deeply rooted illusion. For centuries, even minds as luminous as Isaac Newton and Albert Einstein believed the universe to be still and eternal. Newton saw space as an absolute rigid stage upon which motion occurred. Even Einstein, after unveiling his general theory of relativity, felt compelled to add a cosmological constant, lambda, to keep his universe from collapsing or expanding. Years later, he would quietly refer to this decision as the greatest mistake of his life. The first cracks in this illusion appeared in the 1920s. Astronomer Vesto Slipher noticed that light from distant nebulae was shifted toward the red end of the spectrum. This redshift was a subtle but telling sign. Those distant objects were moving away from us. To understand why this matters, think of the Doppler effect you hear with a passing train. As it approaches, the sound waves are compressed and the pitch rises. As it moves away, the waves stretch and the pitch falls. Light behaves in much the same way. When a galaxy recedes, its light waves stretch, lengthen, and drift toward red. In 1929, Edwin Hubble brought clarity to this discovery by combining distance measurements with velocity. What he found was breathtaking in its simplicity. The farther away a galaxy is, the faster it is moving away from us. This relationship, Hubble's law, was the first compelling evidence that space itself is expanding. Yet the universe left behind an even gentler, more intimate proof of its earliest breath. In 1964, Arno Penzias and Robert Wilson detected a faint, persistent hum coming from every direction in the sky using a radio antenna. It was not interference, not static from Earth. It was the cosmic microwave background, the lingering warmth, the afterglow of the universe's infancy. This radiation is often called the universe's baby photograph, captured when it was only 380,000 years old, at the moment light first traveled freely through expanding space. The remarkable uniformity of this ancient glow raised another question. How could regions of the universe so distant from one another share nearly the same temperature? The answer led scientists to a dramatic idea: cosmic inflation. According to this theory, around 10 to the power of minus 32 seconds after the beginning, an energy field drove the universe to expand faster than the speed of light, increasing its size by an unimaginable factor in an instant. This was the universe's first, most powerful breath, smoothing space-time, calming chaos, and stretching tiny quantum fluctuations into the seeds of galaxies. For decades, scientists believed gravity would eventually slow this expansion, acting like a cosmic brake. Then came a shock. In 1998, two independent teams studying distant Type 1, a supernovae, stellar explosions of remarkably consistent brightness, made a startling discovery. These ancient supernovae appeared dimmer than expected, meaning the galaxies that hosted them were farther away than predicted. The universe was not slowing down. It was accelerating. The unseen force behind this acceleration is known as dark energy. Making up nearly 70% of the universe's total energy content, dark energy possesses a strange property called negative pressure. In Einstein's equations, this pressure causes space to expand rather than collapse. Dark energy is woven into empty space itself. It does not fade as the universe grows. Instead, as more space comes into existence, more dark energy appears, gently pressing the accelerator ever further. And so we return to a deeper question. Why does the universe breathe this way at all? To answer that, scientists are drawn inevitably toward the boundary of time itself, the moment we call the Big Bang. According to standard models, the universe began at a singularity, a point where density and temperature become infinite. Yet this singularity is not a physical object, it is a warning sign. It tells us that our equations have fallen silent. To truly understand today's expansion, we must search for the initial trigger beyond that mathematical wall. Theories such as the Big Bounce suggest that our universe may be the result of a previous one that contracted, reached a quantum limit, and then rebounded, making expansion part of an eternal rhythm of contraction and release. By studying the universe before matter, before light, and perhaps even before time, we are attempting to read the original blueprint of nothingness itself, a state that was not empty, but full of potential, quietly shaping every structure we see today. Our universe is not a static box of stars. It is a living process, an endless breath unfolding across eternity. And here, In the stillness of this night, as you listen, you are part of that breath, moving gently with the expanding fabric of reality itself. Tonight, I light a small fire in my mind and let its quiet warmth guide us beyond the limits of what the eyes can see, toward the deepest frontiers of reality, where we gently begin to redefine nothingness. We often imagine nothingness as an ending, cold, flavorless, and empty. Yet through the lens of modern physics, nothingness reveals itself as a vibrant stage, a vast reservoir of hidden potential from which the eternal radiance of the stars was born. Our story begins thousands of years ago in the contemplative minds of ancient philosophers. Aristotle believed that nature abhors a vacuum, that space itself must always be filled for motion to exist. For centuries, humanity inherited this vision of space as a silent, immutable container. Even Isaac Newton imagined the universe as a fixed stage, with time ticking forward like an absolute metronome, indifferent to all that unfolds within it. That comforting stillness, however, dissolves the moment we descend into the subatomic realm. In the quantum world, Werner Heisenberg revealed a quiet rebellion at the heart of reality. His uncertainty principle tells us that energy at a point can never be forced to absolute zero for any measurable duration. Attempt to still it completely, and the universe responds with restless quantum fluctuations. This is zero-point energy, the perpetual, inaudible hum of existence itself, evidence that nothingness is never truly empty. From this shimmering ocean of energy, pairs of virtual particles and antiparticles continually emerge from nowhere. They appear, briefly entwine in a delicate dance, and vanish again in an instant, repaying their borrowed energy to the vacuum. Nothingness, then, is not an absence, but a living physical state, dynamic and fertile with possibility. The most persuasive proof of this hidden vitality is the Casimir effect. In 1948, physicist Hendrik Casimir predicted that two ultra-thin metal plates placed extremely close together in a vacuum would be gently pulled toward one another. The reason lies in imbalance. More virtual particles press from the outside than from the narrow space between them. This subtle difference produces a real, measurable force. The vacuum, once thought passive and inert, reveals pressure, structure, and the power to curve space-time itself. When I contemplate the universe's ongoing expansion, I feel a deep and humbling awe. We know the universe is breathing, thanks to Edwin Hubble's discovery in 1929. Light from distant galaxies arrives stretched into longer wavelengths, shifted toward red, much like the deepening tone of a train whistle as it moves away. This redshift tells us that galaxies are not simply traveling through space. Space itself is expanding from within, carrying everything along with it. To realize that we stand on a rotating planet, orbiting within a drifting solar system, embedded in a galaxy spinning at hundreds of kilometers per second, is to feel profoundly small and yet intimately connected. We are not standing still. We are participants in an endless cosmic current. This expansion leads us to a paradox. If the universe is growing larger, then long ago it must have been smaller, denser, and hotter. Rewind time far enough, and we arrive at the singularity, a state where density and temperature approach infinity. Yet physicists recognize that infinity is not an answer, but a warning, a sign that our current laws have reached their breaking point. To speak meaningfully about what existed before the Big Bang, we need a deeper framework, a theory of everything capable of uniting gravity with quantum mechanics. Some models, such as the Big Bounce, suggest the universe did not emerge from nothing, but from a previous cosmos that collapsed and rebounded. Others, like Alan Guth's Great Free Lunch idea, propose that the total energy of the universe is exactly zero, with the positive energy of matter perfectly balanced by the negative energy of gravity, allowing the universe to arise as a quantum fluctuation within the void. Today, our universe is dominated by dark energy, which accounts for roughly 68 to 70% of the total cosmic energy budget. This mysterious presence exerts negative pressure, acting as a kind of gentle anti-gravity that drives galaxies apart at ever-increasing speeds. Dark energy is the great breath expanding the chest of space, quietly shaping the ultimate fate of all things. Far in the future, according to the Big Freeze scenario, galaxies will drift beyond visibility, stars will exhaust their fuel, and even black holes will slowly evaporate through Hawking radiation. The universe will approach maximum entropy, a vast ocean of stillness and darkness. And yet, this ceaseless motion, from birth to dissolution, forms a grand symphony of which we have only heard the opening notes. Every atom in your body, the iron in your blood, the calcium in your bones, carries the memory of a journey that began 13.8 billion years ago, forged in stellar furnaces and guided by unseen matter. We are not accidental strangers here. We are the universe awakening, using its own material to contemplate itself. Even if expansion carries us toward solitude, your presence now stands as a quiet triumph of the wondrous imperfection of nothingness. So now, let thoughts of virtual particles, the Casimir effect, and eternal cycles dissolve into the soft mist of sleep. Space is a vast home, and nothingness is not a threat, but a silent promise of new beginnings. Everything moves in its grand rhythm, and so do you. Let your heartbeat fall into harmony with the distant symphony of the stars. Close your eyes. There is nothing left to fear. Only the stillness and the gentle glow of the Milky Way watching over you. The universe was born from a luminous silence, and tonight, it cradles your sleep with boundless care. Sleep well, night travelers.